Okay, this is Dr. Morton. I'm doing this is class day 26. We're still reviewing for the second midterm, and I'm going to do a test which I'll upload the video. Okay, so here we go. So let me put on. Yeah, I think I'm good. Actually, let me get my glasses. Okay, as you know, we're going to have the exam on Wednesday, and we'll have an in-class review, so I encourage you to come to class because it will help you. And then right after we finish, which I think the class is 2 to 3, at 3 you'll be able to, from 3 p.m. after class, right after class, all the way up until 11:59, you can start the test, and you'll have 2 hours to do the test. Okay, that having been said, let me transition. So here's the test, and I'm just going to go through this. I'll probably go through it fairly quickly, and hopefully this will help you. For those of you who might have been in the in-person class this morning at 11, this is the same thing I did in class, so you can probably skip the rest of the video. Well, you can review it too. All right, so there's definitely going to be something like this on the test. And we're going to give you a 4-variable truth table and a 4-variable K-map, and you have to map the truth table to the K-map, identify how many prime implicants, essential and non-essential, and then come up with the SOP and the POS solutions. First, we'll plot the ones, and I usually leave off the zeros. But before I do that, let me just point out that every row in this truth table, the binary value here tells you the row number. So here we have A, B, C, D, or 0, 0, 0. So that's row 0. This is row 1, 2, 3, 4, 5, and so forth. And down here's F, 1, 1, 1, 1. So let me number the little boxes. Remember, we flipped the bottom 2 rows and the rightmost 2 columns. So this is 0. Let's see. Yeah, here we go. 0. 1. Let me see. I need to take this out from under it. Down here is 2. We're going to flip the rows. This is 3. This is 4, 5. Flip the rows. 6, 7. Now we flip the columns. 8, 9. Flip the rows. 10, 11. And finally the last column. 12, 13, 14, and 15. Now that we have these numbers, it's really easy to get the F's in the right place. So we have 1, 1, 0, 1, 0, 0, 0, 0. 8 is 1. And I can always check. Yeah, that's 8. So I know I'm in the right one. This is 9, 10, 11, 12, 0, 13, 0, 14, 1, 15, 1. All right. So now I can see I have a group of 4 here. I have a whole column of 4 here. Now the wraparound, it's pretty easy to see this wraparound group, but what about this wraparound group? Notice I don't just put this one with this one. I have another wraparound group of 4 here, 2 on each side. So if you count them, I have this one, I have this one, I have this column, and this group of 4. And if I write these out, so this group of 4 is going to be, first these columns are A, bottom 2 rows are C, so this is going to be A, C. This wraparound group is going to be B prime, because the outside columns are B prime, and the top 2 rows are C prime, so this is going to be B prime, C prime. And then this group of 2 is also going to be B prime, but this will be B prime D. B prime D. And then, let's see, so that's this group of 4, this group of 4, this column of 4, and this group of 4. So, yeah, so I should have 4 terms. I'm missing one. Oh, the column. The column is A, B prime, this column. Of course, all the C and D drop out, so it's just AB prime, B prime C, B prime D, and AC. All right, so our POS solution, our SOP solution, which is the ones, F is going to equal these terms. So notice when I look at them, the one thing I notice, I can cover all the ones with this wraparound group of 4, this wraparound group of 4, this group of 4. I don't need the vertical column, AB prime. So I can leave out AB prime. It's a consensus term. It's a non-essential. And I have 3 essentials. I have B prime C prime plus B prime D plus A, oh shoot, yeah, plus AC. Right, so B prime is this group of 4 up here. B prime C prime is this group of 4 up here. B prime D is this group of 4. This group of 4 is AC. And the row is AB prime, but I don't need it. So this one is non-essential. The other ones are all essential prime implicants. I have four prime implicants. Okay, good. And we seem to be doing the right thing here. If I wanted to fill out this, which gives us the max term, so I'm going to need to plot the zeros. So I'm going to, down here in this little map, I'm going to plot the zeros and not the ones. So I have a 0 here, and then I have a whole row of zeros. A whole column of zeros. And then I have 2 zeros up here. This whole column is 1s. So let me count them. I have 1, 2, 3, 4, 5, 6, 7. 7 zeros. 1, 2, 3, 4, 5, 6, 7. So that matches. And I should have 1, 2, 3, 4, 5, 6, 7, 8, 9 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that all checks. All right, so this is a group of 4 here, a column of 4 here, and a group of 2 here. So I have 3 prime implicants here. Now in this case, my group of 4, if these were 1s, that would be BC prime. But that makes it B prime plus C. So I'm going to say F equals B prime plus C, quantity times this whole column, because I need it because of this one. So all 3 of these are essential. This 0 is only covered by the column. That 0 only covered by this pair of 2. These 2 zeros only covered by this group of 4. So the column would be A, B prime. So that makes it A prime plus B. And finally, the last term is this one. That's going to be A prime C D prime. So that's going to work out to be A plus C prime plus D. So that's the solution. That's the POS solution. That's the SOP solution. And then if I were to do the min term, the max terms rather, so not 0, not 1. Let's see. Oh, sorry, you can't see that. Let me pull this down. So let me write the max terms. So this is the 0 row. So it's a 1. So no. That's row 1. It's a 1. So no. That's row 2. So we do 2. Not 3, 4. 5, 6, 7, 8, no, not 8, not 9, not 10, not 11, 12, 13, not 14, not 15. So the answer is 2, 4, 5, 6, 7, 12, 13. That is F equals the product of the big M's 2, 4, 5, 6, 7, 12, and 13. That's your shorthand notation. Your expression then is here in the POS form, the max terms, but I've simplified it, of course, with the K-map. So it's B prime plus C, quantity times A prime plus B, quantity times A plus C prime plus D. And here's the POS, B prime C prime plus B prime D plus AC. I don't need the AB prime term because it's not essential, it's this column, and I don't need it. So those are the 2 solutions. So you can see everything there, hopefully. Okay, that's good. All right. Now I'm going to do this decoder problem down here. So here's our decoder. So first thing is we have to make sure. So here's our function. It's in shorthand notation. It's the min terms. In this case, F equals the sum of the little m's 0, 1, 3, 7. Now I don't really need to put them into this truth table because I can just copy them. I can just solve it directly. But I'll write them in here anyway, even though I don't really have to, but maybe it will help some people. Oh, sorry. I wrote a 0 there. That should be a 1. This is a 1. Then 2, 3, 4, 5, 6, and finally 7. And then the rest would be zeros. Okay. Notice my independent variables A, B, and C are going to be connected here, A, B, and C, to my address lines. My chip select has to be grounded for anything to work on this chip at all, because it's a not chip select, if you will, because it's got the bar over it. People use bars. People also use the apostrophe, and sometimes people use a slant like that. They do various things to indicate the not function, like that. But that's okay. So here my ABC connected to my ABC. Remember, these have to be hierarchically correct. If you didn't hook them up in the right order, these wouldn't be ordered 0, 1 through 7. They'd be some mixed up order compared to the truth table anyway. Okay, now how do I solve this problem? I want to get F out. How do I do it? I have to have an AND gate, an OR gate. Have to have an OR gate. So I add an OR gate, and if I want to do a second function, G, I could just add another OR gate as well. I could add a lot of additional OR gates, and as long as my decoder could still drive some large number of inputs, it would be fine. Now, so this is F. Now, how do I hook this up to the decoder? Well, so I need minterms 0, 1, 3, and 7. And these are all the minterms. 0, 1, 2, 3, 4, 5, 6, and 7. I obviously don't need all of them. That would be stupid. That would just be the constant one. I only need the ones for my truth table. In this case are my shorthand notation. 0, 1, 3, and 7. So 0, 1, 3, and 7. Just like that. I don't connect 6, 5, 4, and 2 because there are zeros. So whenever I have these addressed, I want my F to be 0. So I don't connect these, otherwise F would be 1 instead. All right? So remember, there are three possible problems. This decoder, so this one, decoder, a ROM solution, and the MUX. Either a 4-to-1 or an 8-to-1. You can do any 4 variables with a 8-to-1 and 3 variables with a 4-to-1. With the MUX, the 4-to-1 MUX you can do 3, and an 8-to-1 MUX you can do 4. With the ROM, depending on how big the ROM is, you can do whatever. It just, remember, for every additional independent variable, it doubles the size of the ROM for every additional function. And with the decoder and the ROM, you can do multiple functions. Here you just need a new OR gate. There you just need a new column. So every additional function adds a column. Every additional independent variable doubles the size of the ROM. Okay. Next. So we have here a flip-flop. What kind of flip-flop is it? Well, it's got a T input, so it's a T flip-flop. Okay. What kind of flip-flop is it? T flip-flop. What kind of clock? It has a bubble here. Can be filled in or it can be open. Doesn't matter. It means the same thing. It has the edge, little caret that stands for the edge. So it's a falling edge clock because of the bubble. No bubble, it would be a rising edge. Does the flip-flop have a clear knot? Well, actually, it doesn't have a clear knot. It probably was a typo. It probably was supposed to be set knot. Let's say, does the flip-flop have a set knot? Yes, it does. Right here. And it has a bubble, which means the asynchronous input is active, not high, but low because of the bubble. If it didn't have a bubble, then it would be active high. Okay, remember when we talk about limited fan in and limited fan out. In this case, we have limited fan in. So we have, in this case, we have 3 variables, A, B, C, going in here to this AND gate. And all we have to do it with 2 AND gates having only 2 inputs is we just have to have an AND gate here with 2 inputs, A and B. And then we have an output AND gate. We put this in, and then we could just put C directly into this AND gate, or we could have a 2-input AND gate with the inputs tied together, and that could go in. Sometimes we'll do this in order to avoid timing problems. If you don't have this gate, C is going to obviously get to the output gate faster, and so that could cause a problem. What if we have NAND gates instead? Well, okay, with NAND gates, we have to put inverters in this middle layer. Okay, so what we have to do here, We have a NAND gate here. We'll put two inputs here. Let's go ahead. We'll have a NAND gate here, and we'll have two inputs, but we'll tie them together, and we'll drive this with A and B, and this one with C. Okay, so C drives both inputs here, and we only do this for timing. We don't really need it. And now we put a second NAND gate in here, tie the inputs together to make it an inverter, or we could just put an inverter if we want, like this. And then these go to our output NAND gate. So here's a NAND gate serving as an inverter. Here's we just put an inverter. It doesn't really matter. But notice we could actually take all this out, and we could just put C directly in here if we wanted to. That would be fine too. But again, C would get here faster than A and B, because A and B has to go through two gates, or a gate and an inverter, to get down here. So because of that, you could have a little bit of timing problem. So sometimes we'll want to keep things, all the timing nice and consistent. So we'll put in these delays just to keep C arriving at the same time as the A and B's. Okay, here we have a little circuit represented by a K-map. Now, how would we build this circuit? Well, first off, we would simplify it. We know we have to have this group of two and this group of two. There is also another group of two right here, where that's a consensus term. It's not essential, and we're going to talk about that in a minute. We could add that to fix a hazard, but first let's do this. So what is this one? So this is A prime, then C prime D. The B drops. And here we have A prime B C. In this case, the D drops. A prime B C. And then this red one here, the red one would be A prime B D, because the middle two rows are D. Remember the alternate labels. A for these two columns, B for the middle two rows, C for the middle two columns, C for the bottom two rows, and D for the middle two rows. And then obviously top and bottom row would be D prime, left and right columns, leftmost and rightmost columns would be B prime. These two columns would be A prime, top two rows would be C prime. All right. So if we want to draw this now, we just have two AND gates with A prime, C prime, D going in one. We can go A prime, C prime, D, and A prime, B, C going in the other. Going in here. Notice this one has a C prime, this one has a C, and that's where we get in trouble with a hazard. And then, of course, they go to an output OR gate. So if we wanted to fix this hazard, what would happen is, if there's a delay, if we start off, say, with C is 1, so this AND gate is a 1, and this is a 0. When the C switches from a 1 to a 0, this C prime would turn into a 1. But if it has to go through an inverter, the C prime would turn into a 1 slightly later than the C would turn into a 0, because it's directly connected. And this one goes through an inverter. So if that's the case, it's possible that we could be high, drop down, and then come back up, and maybe have like a 5 or a 10 nanosecond little dip here that we didn't want. And we could fix that by adding this term right here with another AND gate, and we bring this in. Now we fixed it. Notice there's no C in this gate. There's an A prime B and a D, and the A prime would have to be a 1, the B would be a 1, and the D would be a 1. And this wouldn't change when the C changes. This would still stay at 1, so that would cause this to stay at 1, and that would go away. All right. Now we have a little bit of VHDL code to deal with here. So we have this, and this is written. This was an old test, so it was written in VHDL. But of course, our test is going to be in Verilog. So here's what this would look like in Verilog. It would be a sine. Let me make sure I'm on here. Yeah, you can see that fine. So it would be a sine. So for this one, a sine equals, and I put a pound 10 here. Sorry, I didn't leave room. A sine pound 10 E. That's my delay. It's the same as the 10 nanosecond delay here. We just write pound 10. E equals A vertical bar B vertical bar C. because that's the syntax for OR in Verilog and also in C. And then we close it with a semicolon. Then our next one, the F one, assign #10 F equals A or Y, semicolon. Here's our delay, 10 nanoseconds. Here it is. Here I barely wrote it in there. I'm sorry. And then finally our last one, assign H, #5 in this case, H equals E. Now we use the and sign, which is an ampersand. E, F, another ampersand, and Z. Now if we draw this circuit, let me just draw it on the back of this. So if we draw this circuit, or maybe I'll draw it on this card. I'll draw it on this card. So let's just draw it right here. So we have an OR gate here with A, B, and C. We have another OR gate with A and Y. These both have 10 nanosecond delays. I'll write 10 in there. And then finally, we have an AND gate here. This goes in, and then we also have the variable Z going in directly. This would be E, and this would be F. And the output here would be H. Now, you can see we have to have 3 ones here in order for H to be a 1. But we only need 1 1 up here to get a 1 here. So we could have, say, A could equal 1, and then B, C, Y could equal 0, but Z would also have to equal 1. The 1 from here would be a 1. The 1 up here through this OR gate would be a 1. Even if A and B and C are 0, Y is 0, but the Z has to also be a 1. So if A is a 1 and Z is a 1, H would equal 1. Okay? But if Z was a 0, then H would be 0. Or if A were 0, you could have B and C being 1s, but if Y and A were both 0s, then this would be a 0, and your AND gate here would put out a 0. Okay? So it's easy to figure out what happens once you draw the circuit. Okay. Now we're going to use, we're going to plot these terms. Now notice this is in SOP form. So we're going to have to plot 1s, because these represent 1s. These are AND gates. If it were in POS form, we'd have to plot 0s, but it's not. It's in SOP. So we're going to plot 1s. So A, C, D. So the first these columns over here are A. The bottom 4 boxes are C in this corner. And D prime is the bottom 2, because the bottom row is D prime. Top row is D prime. But for A, C, D prime, these 2 boxes. It's a 3 variable term, so it should be 2 boxes. Another 3 variable term should be another 2 boxes. So let's see for that. B, middle 2 columns. C, bottom, these 4 right here. And then finally C prime. Oops, let's see. Wait, I did something wrong. D, middle 2 columns is B. Middle 4 are D. And then C prime would be these 2. Okay? Because remember, bottom 2 are C. These 2 are C. Middle 2 are D. These are A. And these are B. All right. So now I've plotted the first 2 terms. Now we have A prime, B prime, C prime, D. So this is just going to be 1 box. Well, I know that the first column is A prime, B prime, so it has to be in the first column. I know the second row is C prime, D, so it has to be this one right there. And then finally A, B, C. So A, these 2 columns. B, the AB is this column. And C would be these 2 boxes right here. These 2. This one already is checked. So now we're left with 0s everywhere else. So we have 0s there, 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 and there. So I'm going to write them. So we have M, 0, not 1, but 2 and 3 and 4, not 5, but 6 and 7. And then 8, 9, 10, or 8, 9, and 11, not 10. 8, 9, not 10, but 11, and 12, not 13, 14, or 15. So those are the zeros. So the zeros are my product of my big M's, the max terms, 0, 2, 3, 4, 6, 7, 8, 9, 11, and 12, those max terms. All right, and that's how I do it. I copy these into the truth table, and then I plot them as ones because it's an SOP form, and then I read off the zeros in my POS shorthand notation. Okay. Again, it's not the expansion; it's just the shorthand notation. All right. Now here we're in POS form. We're going to go to NOR. How do we do that? Double inversion, as you know from your projects. Prime. We take this and partially expand it. We don't go inside these parentheses, but we do put pluses in between them all because we have to change the ands into ors, and we have to prime the variables. We'll treat the whole parentheses as a single variable. And then we get rid of these inner parentheses and we just have the external. So we have NOR gate, NOR gate, NOR gate, NOR gate, and one big final output NOR gate with 1, 2, 3, 4 inputs from these. And that's that. All right, final problem. Final problem is this final one here. And so I'm going to shine it over here a little bit. Okay, so notice using the D flip-flop picture. Okay, so it's a D flip-flop. Write in the tracing for Q in the timing diagram. Assume the delay for outputs to change after the active edge of the clock or the asynchronous set is 10 nanoseconds. Assume setup and hold times can be ignored and that Q is 0 at the beginning. So we know Q starts here at 0. So let's first look at this. So what kind of clock does it have? Well, it has a falling edge clock. And the set, is the set active high or active low? Well, there's no bubble, so the set is active high. So we color in everywhere where the set is going to be active. So it's going to be active where it's 1. So that's going to be in these little areas right here. And here it's going to block any active any clock edges, any falling edges. So I take all these other edges and I'm going to mark and I'm going to pull them down here. But this one's blocked. So this is the falling edge, but it's blocked, falling edge, but it's blocked. This one not blocked. This one blocked. This one not blocked. I didn't draw it very straight. And this one not blocked. Okay, so, all right, there we go. Now, what is the value of D at this active edge? This active edge, D is a 1. What is the value of D here? Oh, here's where my asynchronous input is asserted. So I'm going to draw a line for that too. And here's where it's asserted again. Now I don't care about where it's deasserted because that doesn't do anything directly. I have to wait for the clock edge. Here, my D is a 0. Here my D is a 1, and here my D is a 0. All right. Now I know that these lines are where I assert the set or the falling edge happens, but that's not where Q changes. Remember, there's a 10 nanosecond delay, so I have to go out here, and so I'm going to mark a little mark right here. I know Q can change here. Q could possibly change here, possibly change here, possibly change here, possibly change here, and possibly change here. So let's see what actually happens. Here, when the clock edge hits, D is a 1, so at this point, I know that my D is going to go up to 1. Now I know it can't change to this next red mark. And here I have a set. Well, the set's going to make it be 1 too, so it's just going to stay at 1 all the way down to this red mark. Now at the clock edge, D was 0, so at this red mark, it's going to go to 0. Here's my set, so at this red mark, it's going back to 1. And it's going to stay there until this red mark, again, 10 nanoseconds after the active edge of the clock. It's a 1, so it's not going to change. Then it's going to go to here. Oh, it's a 0, so it is going to go down to 0 and continue. So notice we have a rising edge here at 40 nanoseconds. We have a falling edge here at 160. We have a rising edge at 180. We have a falling edge at 280. So I might ask you about those things. Okay. notice these changes can only occur at these red marks, but here no change occurs because it's already 1 and the set just keeps it at 1. Here, no change occurs because the set made it 1 and then that clock hit, but D was a 1, so it stayed at 1. But here, D was a 0 at the falling edge, and now it drops 10 nanoseconds later to 0. Okay, so that solves that problem. Okay, hopefully that makes good sense to you. All right. Now, okay, let me just say a few things, general type things. Let's see. So first off, we should always remember that you should always keep in mind your SOP form is based on the min terms, based on the 1s. Your POS solution is based on the 0s, and it's the max terms. When you're making hardware, you should always keep in mind that we typically do our design in SOP or POS, but then we switch it to maybe NAND, or NOR, which are the commonly used forms to make integrated circuits. And that's just because we like to have the same gates, because it makes it more consistent timing-wise. We remember if you take the AND gate, OR gate, NAND gate, and NOR gate, those 4 gates, you can make 16 different 2-layer combinations out of those gates. You can do AND, OR, and NAND, and NOR. You can do OR, AND, or NAND, or NOR, and so forth. But of those 16, only 8 are really useful, and that can implement any logic function in a 2-layer net. The other 8 can implement some functions, but not all functions. So that's the difference. Because of that, we pay attention to 4 of the 8 that are functionally complete sets of gates. Okay, and what are those 4? Those 4 are the SOP and the POS plus NAND, and NOR. Those are the important ones. And the others, we talked about them, but we really didn't. I didn't ask you to learn them or memorize them. You don't really have to know them. You can always look them up if you need to find them for some reason. But be aware, there are a total of 8 that are functionally complete out of the 16 possible combinations using those 4 gates. But only 4 of them are commonly used. We typically use SOP and POS to do our design, and then we change it to NAND, or NOR, depending on our target hardware. Okay, so that should explain some things. Let me see. Okay, so let's see, a couple other things. So we talked about limited fan-in, and you remember with AND and OR, you just have to add the gates, but with NAND and NOR, you have to put inverters in between. Let's see, what else? Remember our general usage thoughts for flip-flops. So we talked about 4 flip-flops, well, counting RS latches. So RS latch and 3 flip-flops. So the flip-flops are T, D, and JK. So there are a couple of things you should know just generally. Remember that the RS latch is typically the fastest one, and we might use that in a system with a very high-speed clock where we need a really fast latch or flip-flop. So we normally refer to the RS as a latch. When we compare T, JK, and D, most things are made out of Ds. And the T really doesn't exist, but we make them from JKs. We might make the T's and use them in counters, but basically the T doesn't get that much play. So you're really concerned about JKs and Ds. JKs often will result in less total hardware for your state machine to drive those inputs, but there's going to be more wires running around. This is especially a problem if you're using a ROM for your solution, because if you're using a ROM and you're using D flip-flops, you only need 1 column for the D output for each of the flip-flops, or the D input rather, I should say, the D comes out of the ROM and goes into the flip-flop basically, and that you only need one column if you're using Ds. But if you're using JKs, now you need 2 columns for every flip-flop. So, and there's also more wiring. But if you're not using a ROM, say you're using hardware, you're using a bunch of gates to drive your inputs, normally there are less gates involved in the JK flip-flops because there's a lot more don't cares, and typically it just works out to fewer gates. So because of that, if we're not using a ROM, sometimes we will choose JKs as long as we're not worried about more wiring. So sometimes that's an issue, sometimes not. And often that wiring is in the form of, in the FPGA, it's in a switch matrix, and actually in an FPGA, say the Xilinx FPGAs, they don't really use an input set of gates and an output gate per se. They use lookup tables or truth tables directly, which are really ROMs. They typically use ROMs. So we don't normally worry about simplifying things at all when we're programming an FPGA. In fact, we let the FPGA worry about it anyway, but that we let the synthesizer software worry about that. Okay. So let's see what else. Well, let me see. Yeah, when we use AND and ORs, we do have to also include the possibility of having to have inverters. Like I say, most of the time, if we have registers that are driving our network, a lot of times those registers, well, they're just flip-flops, and a lot of times those flip-flops will have a Q and a Q prime output. So most of our variables will have a prime output as well. So often we don't have to have inverters, but if we did, we would have to. If we didn't have that, we'd have to have inverters. Okay, let's see. Let's see, what are some other things? You remember that if you're going to use NAND, you want to do the SOP form. If you want to do NOR, you have to do the POS, the max terms, the zeros. In a ROM, every time we add an additional independent variable, it doubles the size of the ROM. Every time we add an additional output function, it adds 1 column to the ROM. So let's see. So if you have a 4-to-1 MUX, you can do a 3-variable problem. I think I went over this already. And a 4-to-1, you can do a 4 independent variable problem. Yeah. So if you're doing a design and you want to check it to see if it works, you can always put into a logic simulator like you did with your design for the group project. Okay, I think that's pretty much everything. I think I covered most everything that's going to be on the test. We will do some more review on Wednesday. You guys should be really pumped and prepared, assuming you're keeping up and looking at the videos and staying up with things. By the way, I thought everybody did a great job on the project presentations, so I was definitely pleased. Okay, with that, I'll quit.